Hello everyone, and welcome to The Explainer. Now usually, we'd start off with a nice, tidy agenda. But today, we're tossing that right out the window. We literally need to plunge straight into a massive, totally mind-bending mystery about the universe we live in. We usually look up at the night sky and think of it as this perfectly predictable, beautifully stable clockwork system. But what if I told you that right beneath that calm exterior lies a terrifying, completely invisible threat?
It's a pretty provocative question, isn't it? Is our solar system a ticking time bomb? I kind of want to shatter your assumption of a peaceful, stable cosmic neighborhood right out of the gate here. The reality, at least according to some insanely complex astrophysics, is that our seemingly solid, dependable world is actually dancing right on the razor's edge of ultimate destruction. And the craziest part? The trigger for this catastrophe has been hiding in plain sight the whole time.
Okay, let's dive into this. Part 1. The illusion of a clockwork universe.
So, to really understand this hidden threat, we first have to look at the baseline we've all been taught for centuries, right? Isaac Newton's reliable clockwork physics. Under purely Newtonian physics, if you isolate just a single planet and the sun, the math is, well, it's absolutely beautiful. The planet's orbit forms a flawless, eternal elliptical loop. It just keeps going around and around on that exact same path. There are literally no surprises. If our solar system was just the Earth and the Sun, we would be entirely safe forever, period.
But we aren't alone, which brings us to part 2, the hidden chaos of gravity.
So here's the fatal flaw in Newton's perfect little picture. Planets aren't out there by themselves. They actually pull on one another. And the real danger here lies in a fascinating concept called resonance. Resonance happens when the orbital frequencies of two planets magically align mathematically, like when small whole number ratios start linking their movements. When this happens, a tiny gravitational pull doesn't just happen randomly anymore. It happens at the exact same point in the orbit, over and over and over again, eventually accumulating into a massive system-altering force. Think of it kind of like a cosmic puppeteer. Jupiter, with its absolutely massive gravity, can rhythmically tug on a tiny planet like Mercury all the way from across the solar system.
And this brilliantly illustrates what that actually looks like. Because of all these little gravitational perturbations from other planets, a planet's orbit doesn't stay locked in place perfectly. As you track it over thousands of years, the long axis of that orbital ellipse actually rotates. It shifts completely unpredictably over time. Basically, it's wobbling. And when that resonance we just talked about locks in, well, that wobble can quickly spiral totally out of control.
Which leads us directly into part 3, a recipe for cosmic disaster.
Now you might be thinking, this is all just theoretical math, right? Well, no. Astronomers Jacques Lascar and Michael Gastineau actually used supercomputers to literally predict the ultimate future of our solar system. But predicting a chaotic system is insanely difficult. To mathematically calculate the solar system's movements up to 40 million years from now, you need to know the current exact position of the planets down to an error margin of just 15 meters. Okay, but what if you want to predict up to 60 million years? You have to know where the planets are right now, down to 15 millimeters. Because of this chaos, calculating past 60 million years is technically impossible. Literally, a 15 millimeter mistake today completely changes the entire outcome of the solar system.
So how do you bypass this impossible 15 millimeter problem? Well, Lascar and Gastineau took a statistical approach. They set up the current solar system, made microscopic variations to the starting positions, and ran 2,500 different possible futures using strictly pure classic Newtonian physics. They basically simulated the end of the world thousands of times over to see what would happen.
And here is the first massive shock. In about 1% of these pure Newtonian futures, Mercury goes completely rogue. Because of that rhythmic resonance with Jupiter we talked about, Mercury's orbit gets incredibly stretched out over time. Its orbital eccentricity dangerously exceeds a value of 0.7. Now, what does that mean? It means its path becomes a highly stretched, super elongated oval. And once it hits that extreme shape, it actually starts crossing the paths of the other inner planets.
So the absolutely crucial point here is that Mercury isn't just some tiny rock that gets quietly tossed out into the void. Oh no, it acts as a massive trigger. When its orbit stretches past that 0.7 mark, it totally rips apart the stability of the entire inner solar system. First, it pulls on Venus. Then, Venus's orbit destabilizes, which then completely throws Earth's orbit into chaos, and finally Mars gets dragged right into the fray. It's an apocalyptic, system-wide domino effect.
The climax of these Newtonian simulations is, well, it's nothing short of horrifying. In those 2,500 simulated futures, Mercury obliterates Venus 86 times, and it crashes directly into Earth 34 times. Let that sink in. Under pure Newton math, our planet is basically playing a cosmic waiting game with absolute destruction.
But wait, part 4, Einstein saves the world.
Obviously, we are still here, right? So why? Well, a tiny microscopic detail from 20th century physics swoops in as the ultimate plot twist. It turns out Albert Einstein's theory of general relativity is the literal savior of our planet. As the researchers noted, if it weren't for the incredibly slight effect of Einstein's corrections to gravity, humanity likely would not exist in this universe at all.
Now, what's truly fascinating about this is exactly how unimaginably small this correction actually is. General relativity tells us that massive objects warp spacetime. For Mercury, which is moving really fast deep down in the sun's gravity well, this introduces a tiny mathematical correction factor, velocity squared over the speed of light squared. We are talking about a factor of roughly 10 to the negative 8th power. That is 0.00000001. It's a microscopic warp in spacetime, but it alters Mercury's path just enough to matter.
Let's compare these two cosmic fates side by side. Under Newton's math, the resonance between Jupiter and Mercury goes completely unchecked, pulling the planets into those dozens of fatal collisions we saw. But under Einstein's relativity, that tiny, practically invisible warp in spacetime shifts Mercury's orbit just a fraction of a hair. It acts like a cosmic speed bump. It desyncs Jupiter and Mercury, completely disrupting that deadly resonance. When the researchers ran the exact same 2,500 simulations again, but this time with Einstein's equations included, the collisions basically vanished. Out of all those futures, there was only one single near miss where Mercury exceeded that dangerous 0.7 threshold.
And that brings us to our final takeaway. Part 5, our fragile cosmic oasis. When you really step back and think about the sheer mathematical luck required for this system to stay together, it forces you to ask, why does this matter for you and me? It means that our totally solid, dependable, everyday world is actually living right on the razor's edge of cosmic chaos. Our planet's survival over the next 4 billion years, until the sun eventually expands anyway, doesn't actually come from some unbreakable, bulletproof law of perfect orbits. It hinges entirely on a fragile, totally bizarre relativistic quirk of spacetime that just barely keeps Mercury in check. It honestly leaves you in awe, doesn't it? So, I want to leave you with this final thought today. We look out into the deep universe hunting for other planetary systems, right? Looking for signs of life. But if our own existence relied entirely on a microscopic, 1 in a million warp in spacetime just to stop our planets from playing a deadly game of cosmic billiards, how many other worlds out there in the dark simply weren't so lucky? Keep looking up, folks, and never ever take our stable little sky for granted. Catch you next time.